This video is going to go through and review some of our exponential growth, a lot of our differential equations applications that we focus a little bit more on in Calc BC than we did in AB. Now this particular video, the two topics are going to focus on exponential growth, which is definitely a Calc 1 topic. You should have a lot of experience with exponential growth. And then Newton's law of cooling, which even though it does tend to show up on the syllabus of AB calculus, it tends to not show up much in a testing environment until BC calculus. So we'll do one of each and try to do ones that are very similar to what you'll see on a quiz. So first one talks about the rate, the number of bacteria growing at a rate proportional to how many there are in the environment. That is an important statement because that is what indicates that it's exponential growth. The problem won't actually say that it grows exponentially or use the exponential growth model. They'll usually write a sentence like that first one, that something is growing or decaying at a rate proportional to how much is there. When you see that, then you automatically can go to our exponential growth model, which is y equals c e to the kt. You will never be asked to actually derive that model by separation of variables, although we now know how to do that. You can go straight there. This particular problem says in an experiment we have 20 bacteria present after 3 hours, 100 present after 5 hours. This question actually does not give the initial amount. It wants us to find that. It wants us to find the c-value. And then at the end, we're going to figure out how many were present after 12 hours. So we're going to start by taking these pieces of information and writing it as two separate growth equations. For the first equation, we know that we have 20 bacteria after 3 hours. So we get this equation, and we know that there are 100 after 5 hours. We actually did a problem like this last year in calculus, but it was with fruit flies, but it was the same type of situation. We need to find c. So here it's like we're solving a systems of equations, and I think the easiest way to do this is to solve both equations for c. So in the first one, c equals 20 divided by e to the 3k, and in the second one, c equals 100 divided by e to the 5k. This is not the only way to go about solving it, but this is the way that I kind of think when I look at this. I'm going to set those two equal to each other so I can solve for k. So 20 over e to the 3k equals 100 over e to the 5k. Cross multiply, I get 20 e to the 5k equals 100 e to the 3k. I'm going to divide both sides by 20. So I get e to the 5k equals 5 e to the 3k. I'm going to divide both sides by e to the 3k. Here I'm going to use exponent rules. I can subtract 5k minus 3k since the bases are the same. So I get e to the 2k equals 5. Here now I need a calculator, so I have the natural log of both sides. And then I'm going to divide by 2. So I can say that k, either I can write it as exactly the natural log of 5 all divided by 2. Or I can go to my calculator and plug it in. I've already done this, so I had both of them ready. It ends up being approximately 0.8047. You can use the exact, or if you plan on using the decimal further, it is a good idea to store it in your calculator. To answer the first question, I want to know how many are present initially. So now I'm going to take this k value, and I can either put it into this equation or this equation. It does not matter. I'll go with the one with the smaller numbers. So I have 20 over e to the 3 times that k value that we just found. Since I already have it on my calculator, I'm going to multiply by 3. I'm going to take e to that power. I'm going to take 20 divided by that answer, and I get c to be approximately 1.788, kind of repeating. Now, I don't know if you can have part of a bacteria, but rather than round it, because I know I'm not done with the problem, I'm going to leave it like that. You could also store that one if you want to store it as a second value. Now you have k possibly stored and you have c possibly stored. So we have just under 2 bacteria, or you could round it to the nearest bacteria, saying 2 bacteria at the start of this particular experiment. Now to answer the second question, how many are going to be present after 12 hours? Well, I have y equals, I just figured out what c was, so I can either have it stored in my calculator, or I could just put the letter c down knowing that this is what c is. E to the 12 times the k value that, again, I also have stored. So I have a lot of decimals, and storing here prevents any type of rounding error. Plug it all into your calculator. You should get, and I am going to round to the nearest one here, 27,951 bacteria. It was 27,950.849. Oftentimes the problem will ask you, especially when you're dealing with real life, to round to the nearest whole number depending on what the particular quantity is that you're looking at. So that's an exponential growth. You should be able with exponential growth to not only find c-values, you should be able to figure out a particular time when a population gets to a certain amount. You should be able to figure out how much after a certain amount of time. You should be able to find the k-value. Sometimes they'll make it really easy and they'll give you the k-value. They'll actually tell you how much something is growing by. But this kind of shows you the highest amount of work that you would have to do in a problem. Second example is Newton's law of cooling. So I'm going to do a quick recap just to remind you of what we talked about in class, what all happened with Newton's law of cooling. First, we had kind of our differential equation. The idea is the rate that the temperature is changing is directly proportional to the difference between the temperature of that particular object, whether in this case it's a cup of soup or a cup of coffee or the dead body that we had in class, and then minus the surroundings, the difference between the temperature of the object and the surrounding air. And they have to tell you what type of environment it's put in. And in this particular one, you see we're taking a cup of soup out of the microwave. Soup's 160 degrees Fahrenheit. It's too hot. So we put it into a surroundings, an environment of 55 degrees Fahrenheit. So they have to give you that S, that surrounding temperature. Now, we went through and separated variables. I'm just going to talk very briefly about this and then also show you what you could skip. So this is what ended up happening when we separated variables. And then we integrated, and we took the natural log, and then we exponentiated. And in the end, you should end up with a formula that looks like this. So I'm skipping some steps here, taking the same steps that we would have done in class. Integrate, natural log, use E on both sides. And this is what you end up with for your equation. The S, again, is your surrounding air temperature. Your C value is not the initial temperature of this, in this case, the cup of soup. Instead, your C value is the difference between the cup of soup, in this case, and the surrounding air. And the way you get that, if you can't remember that, is you plug in 0 and say, okay, at time 0, I'm 160 degrees. So if I put 160 degrees in here, when I put 0 in for time, I'm going to be left with C, because e to the 0 is just 1, plus my surroundings are 55 degrees, so we end up getting C to be 105. So if you can't remember that C is the difference between the two, you can put your initial time in and your initial temperature, and you'll get that either way. So we've got our equation. C is 105. E to the kT plus my surrounding air temperature is 55 degrees. So here is my basic equation, my general equation for the cup of soup that I'm taking out of the microwave and cooling down. Now I have to have enough information to figure out K, and that's what the next line says. After 5 minutes, the soup has cooled down to 125 degrees. So I'm going to put 125 in for my capital T. I'm going to put in time of 5, so e to the 5k plus 75. Here now is where the calculator work starts. So I'm going to show a little bit of this, but most of it's done on your calculator. So we have 125, sorry about that. I don't know why I wrote 75 for a second there. Minus 55, 125 minus 55, which is 70, equals 105 e to the 5k. Divide by 105. Take the natural log of both sides, divide them by 5, and again, I'm doing all of this on my calculator, so I'm going pretty quickly, and I got a K value of around negative 0.08, and it had several digits, and I stored it to make sure that I have that K value, so no matter what they ask, I am ready for it. And then I want to answer the final question. When is the soup going to cool down to 80 degrees? Well, that means I need my temperature to be 80. My C value, as I said, is 105. E to the, now I know what K is, but I usually just kind of write it like this, saying I already figured it out. I'm not going to rewrite it. T plus 55. Subtract 55. Subtract 55. Then I have my 25 equals 105 e to the kt. Divide by 105, take the natural log of both sides, divide by the K value that I stored in my calculator all along, and what I find out is it takes about 17.697 minutes, or if they say round to the nearest minute, about 18 minutes for my soup to cool off down to 80 degrees Fahrenheit. So it takes you through what you're looking at. Again, you do not need to actually derive the equation yourself, meaning you don't have to go through the separation and integration, things like that. But you should understand how it works. There are problems that, as I mentioned with exponential growth, that are a little easier. Well, they'll actually give you that K value. So those save you some time. You already know your K value. Other than that, this is really, again, kind of the longest problem that you would have to work with, where you have to not only come up with your equation, but then use it to answer a question, try to figure out when the soup is cooling. They also can ask a question such as, well, after 10 minutes, what's the temperature of the soup? So those are a little easier, where you're just plugging something in for time. This is very similar to like the turkey example that we did in class, or the coffee example. We tend to deal a lot with food and drinks with these, because those are the types of things that you're either heating up or cooling down in a particular environment. If you can do this problem, you can do the exponential growth problem. That covers about a third to a half of your quiz coming up with the type of questions that will be on it.